Well, hello everybody and welcome back. All right, today we have section 2 of unit 2. All right, unit 2 is one-dimensional motion, and section 2 we're discussing velocity and acceleration. All right, so here are some of the key terms that we're going to be using throughout the section, along with all the things that we learned in the last section, including distance and displacement, and how important direction really is to all of these three concepts. We start with average speed and average velocity. So these two things are very similar to each other. We're really talking about how fast an object is moving from one place to another. All right. Now we can describe that motion two different ways. And remember, when something moves, it means it changes position. It goes from one place to another. Now it does that by taking a path. And remember, distance is the length of the path. But we can also talk about this in terms of a change in position, right? And change in position here is displacement. All right, so the main difference between average speed and average velocity, and they're very, very similar to each other, is that one uses distance in its calculation and the other one uses displacement in its calculation. So to look at these two equations really does tell us the main difference between the two. All right, speed does not use direction. Velocity does use direction. All right. And so as we look at these equations, let's just kind of point out all of the important players that are here. S, that's going to be speed. All right. D, that's going to be distance like before. T, this is going to be the amount of time. All right. Now notice how a couple of these differ in the next row down. When we look at average velocity, we're talking about rates of change in um, for each one of these terms, but uh, one of them is talking about a change in position, while the other one is talking about changing the length of the path or the distance. All right. So here we have v. This is our velocity. All right. Delta x, remember, this is displacement. Now, keep in mind, we have at least two different directions of displacement that we've discussed. There's delta x, which is horizontal displacement, but we could just as easily rewrite this equation with the vertical position. So we could just as easily write this as delta y over delta t, all right? So that's a possibility as well. It's just that if we were to write every equation that we have with x's and y's, we'd have twice as many equations and things would get a little bit cumbersome. There just would be so many things to look at. So remember, anywhere that you see an x, you can replace it with a y. All right, so we have average velocity. All right, that's our v. We have displacement delta x, all right, which is a change in position. Right? Don't forget, that's the definition of displacement, change in position. So flat out in this definition, the rate of change in position automatically means we're using displacement. It also tells us that there's guaranteed to be a direction because displacement has direction as a part of it. All right. Now down here we see delta t. All right. Now that's a funky one because why isn't it just a t? So here we're talking about the amount of time it takes to change our position. All right, well, delta t gives us a little bit more information. We call this the time interval. All right, and just like any other change, the way we would calculate a change in time or the time interval would be to take the final time minus the initial time. Well, that's weird. What do you mean final time and initial time? Well, think about a stopwatch, right? So we have a stopwatch, and where does it always start? It always starts at 0 seconds, right? So at 0 seconds, that's our starting time. That would be our initial time. And as we let this thing go on, maybe we stop it at 30 seconds. And like, bam, that's our final time. So our initial time is 0. Our final time is 30. All right. Now we can, most of the time, 90% of the time, we're going to start our clocks from 0. But just in case we don't, we can use this example to kind of help us out. What if we started our stopwatch from 30 and then we let it count off until it got to 45? Well, in this case, the time interval would be the difference between the two. It would tell us that we would have our 45 seconds for our final time, our initial time would be 30 seconds, and there we have a difference or a time interval of 15 seconds. All right, so what time interval allows us to do is to have a starting time and an ending time, much like a position in that way. All right, so those are the two main ideas right there with velocity and speed. they are very, very similar to each other. Let's talk about some of those similarities using their units, all right? So we're talking about how fast things are moving, all right? And we already said that they have different ways of moving in the sense that we can calculate distance or displacement, all right? But when we do this calculation, if we're talking about units, what are the units for speed? That's the question, units. Well, what we'll do here is we'll look at the units for the things that go into calculating it. So for distance, we're talking about meters. And for time, the units are going to be seconds. So if we divide those two, we get meters over seconds or meters per second. So those are the units for speed, meters per second. It is giving us a distance that is covered in a specific period of time. If we look at displacement and average velocity, again, we see that our units are meters, and for time, our units, again, are seconds. And so we see, again, that we have the same units, meters per second, for velocity that we did for speed. So are these things the same? No. The main difference between these two is that speed uses distance, which does not have direction, while velocity uses displacement, which does have direction. So distance does not have direction. Velocity has displacement, which does use direction. So that extra piece of information is going to allow us to do things with calculations that we couldn't do with distance. All right. We're going to be able to be much more specific with our answers. Now, acceleration is a different animal entirely. These two guys up here, all right, they have the same units. So they're very, very close to being the exact same thing. The only difference is the distance versus displacement thing. But acceleration is a different story entirely. Here, we're talking about changing our velocity, all right? So here, if we change our velocity, that means we are going to have a different value for our velocity. So how do you do that? Well, acceleration happens when you have objects that speed up or when objects slow down. Or, and this is a special one, and we'll discuss this later in the year, when objects change direction. This is a different type of acceleration, but it is an acceleration, all right? And so in these cases, we don't have an object traveling along at a very constant meter per second. We're actually changing that velocity, and it's getting faster or it's getting slower, all right? And so in those cases, when we're talking about a change in velocity, we can calculate this delta V just like every other change that we do. If there's a change in any variable, then we always take the final value minus the initial value. So a change in velocity here is V final minus V initial, or our initial our final velocity minus our initial velocity. So this shows that we are changing our velocity. Our starting velocity is different from our ending velocity. And that's essentially what acceleration is a change in velocity, all right? So A is going to stand for acceleration. V is going to be, delta V is going to be our change in velocity, all right? We see that right here in our definition. And delta t is still going to be our time interval. So we're going to change our velocity in a specific period of time. So if I look at the units, all right, we have meters per second for velocity. We have seconds for time. And that gives us a very interesting unit. This is meters per second, all right? Otherwise known as meters per second squared. So what's that telling us? It's telling us how much our meters per second are changing each second, all right? We write it for convenience as a meters per second squared. We can show that through dimensional analysis. All right, so some important notes to make about the directions of these things, all right? Remember, speed does not have direction because it uses distance, all right? And we call these things that don't have direction, all right? We call those scalar quantities, all right? So a scalar quantity is one that has a magnitude, a number, but no direction. This would look like something like maybe 10 meters or maybe 10 meters per second or even 10 meters per second squared. None of those have direction. But velocity and acceleration both use displacement as a part of them. And so they do have direction. And we would see an extra piece of information. So vectors are things that have both a magnitude, that's my 10 meters, but then also a direction, like 10 meters west. So here's my magnitude, and here is my direction. So displacement is a vector. Velocity is a vector. So we could have 10 meters per second west. And acceleration can be a vector, 10 meters per second squared west. But notice they all have direction and magnitude. All right. So with this extra information, we ought to be able to do some extra calculations. So what we're going to do next is what we call a ticker tape diagram. And in this ticker tape diagram, we're going to try to represent this motion as basically a set of dots. And these dots represent the displacement at specific times when an object is moving. So right now we have a constant velocity of positive 1 meter per second. So first, I just want to kind of identify. We know that this is a velocity because of the units, meters per second. All right, meters per second. I also know something else about this velocity, in that it's in the right direction. So it's pointed rightward. How do I know that? That's because of the positive here. So that's what the extra information of giving us a direction is going to have us get from velocity that we can't get from something else, like speed. So if I let this object go, this is what constant velocity looks like. The object is moving steadily across the screen, where it's covering the same displacements in the same period of time. Say equal displacement in equal time intervals. So essentially what we're saying here at 1 meter per second is that we're saying each second this object will have a displacement of 1 meter. Okay, so we can show this as like our ticker tape diagram. And the way that we do this is show the positions of the object at different times. So at our very starting point, and since we're going to have several of these, I'm going to call it x sub 0, so a subscript of 0. We're going to be located at 0 meters. And this fire truck will be moving off to the right. Well, at 0 seconds, it is located at 0 meters. After 1 second, we'll call this T1, 1 second, all right, then this constant velocity is telling us, all right, that the fire truck has moved 1 meter in 1 second. So since 1 second has gone by, then this object has gone 1 meter, and it's now located 1 meter to the right. At 2 seconds, we see that it has moved another meter, all right, and it's now located at 2 meters away from our starting point. And I can think you can see the pattern now. At 3 seconds, then we are now 3 meters away from our starting point. All right. And so we can look at this and notice a few things. Each one of these displacements, each one of these positions at each one of these times is equally spaced. All right. Constant velocity, constant, means it's unchanging. And so this is telling us that for every second that goes by, this object will have traveled 1 more meter. We can get this through a little bit of easy calculation too, all right? So if I look at the values that I have, all right, what I want to kind of point out here to start with is our equation. Remember, velocity is a displacement in a time interval, all right? And so what I can do with that is look at a specific time interval. So I'm going to call this my starting point, my 0 seconds, and I'm going to go up to this first second right here, all right? And so I notice a few things. My time interval starts at 0 seconds and ends at 1 second, all right? And my position starts at 0 meters and ends at 1 meter. So if I use my equation that velocity is displacement over time, I'm going to do a little substitution here. Remember, delta x is the same thing as x final minus x initial. right? And delta t is the same thing as t final minus t initial. And so if I substitute over here, all right, my final position, this is the part at the end, or where I made it to. So I'm going to go with x1, that's 1 meter. And I'm going to subtract my initial position, which is right there, that is 0 meters. All right. And I'm going to divide that by the difference in the times, which is 1 second and 0 seconds. And what do I find here? Up on top, I have 1 meter minus 0 meters is 1 meter. On the bottom, I have 1 second minus 0 seconds is 1 second. And what do I get? I get a positive 1 meter per second as my final answer. So there it is. I get the velocity that I already knew it was, but that's what that means. If this displacement isn't equal throughout these time periods, then if I pick somewhere else, it won't be the same thing. It won't be 1 meter per second, but I can guarantee that it will be. I'm going to pick a weird interval. I'm going to go from T1 all the way over to T3 here. All right. So now my interval has changed. My starting value, all right, is 1 meter, and my ending value is 3 meters for my position, and my starting time is 1 second, and my ending time is 3 seconds. All right, so I should be able to pick any time interval that I want, no matter how big or how small, and I should get the same velocity no matter what. All right, and so if I do this, let's see what I get. I get 3 meters minus my 1 meter. All right, so 3 meters is my ending value. 1 meter is my starting value now. All right, so I can move things around, but they still have to stay in chronological order. 3 seconds down here is my ending time. 1 second is my beginning time. And what do I find? I get 3 meters minus 1 meter on the top, that's 2 meters. 3 seconds minus 1 second on the bottom, that's 2 seconds. And bam, I get it again. Positive 1 meter per second. So it doesn't matter what time interval I choose. This is giving the ratio. This is essentially how many meters are traveled each second. So how much is traveled in each time. Notice they're all equally spaced. There's 1 meter in between every one of these seconds. There would be 2 meters in between each 2 seconds, so on and so forth. That's what a constant velocity of 1 meter per second tells us. All right. What happens if I change this to a negative? All right, so what happens if this goes from positive 1 meters per second to negative 1 meters per second? The only thing that's changing here is the direction. So I start over here at 0 meters, all right, and 0 seconds, but now I'm moving to the left, all right? And so at 1 second later, I'm now located at negative 1 meters, all right? And at 2 seconds, I'm at negative 2 meters. So the spacing is still 1 meter per second, all right? The spacing is still 1 meter each second, but now we see that it's in the negative direction. And we could do the same activity that we did in the previous one, and I'm just going to pick the starting and ending points being there and there. All right, so at x2 and x0, that's being my initial. Then I can calculate my velocity. Remember, it's, final position minus initial position divided by final time minus initial time. All right, so my final position is negative 2 meters. Initial was 0 meters. 2 seconds and 0 seconds. And what do I get? I get negative 2 meters over 2 seconds, which is negative 1 meter per second. So the only thing this changes, this is still equally spaced displacements in equal time periods, all right, in equal time intervals. It's just now traveling in the negative direction, all right? So what are some things that we can kind of look at here? What do we notice about the distribution and regularity of the position of the dots for constant velocity? This is essentially asking us, when we talk about distribution and regularity, are they equally spaced or are they not equally spaced? Yes, they are equally spaced, all right? So we will see this thing. So when we look at these dots and we look at these positions in equal time periods, we should see that they have the same displacement between them. So what does the positive and negative tell us about the velocity of the object? This is about direction the object is moving. All right. Does the positive or negative affect the distribution or the regularity? So does a positive or negative change whether or not they're equally spaced? No, it does not change it. They are still equally spaced. It's just that the object is moving in either the left direction or the right direction, or the up direction or the down direction, right? Or maybe north, south, east, or west, but that's all it is. It's just direction. It does not change the fact that they are equally spaced, all right? Would a greater magnitude, what would that do for the velocity? So if I had a bigger velocity, say of like 2 meters per second, let's make it crazy. Let's make it 10 meters per second. What does that do to the distribution of the dots? Well, we get a larger space in between. Because essentially what we're saying is it's covering more displacement in 1 second or one period of time. So we get a greater magnitude for our velocity means that the dots are more spaced out. And if we had a smaller magnitude, that would mean a smaller velocity, all right? Then the dots would be closer together. All right, so very small velocities, we're covering small displacements, so the dots are close together. Very large velocities, then we see that the dots are spaced out quite a bit because they're covering large displacements. All right, so this was our discussion about velocity. We're going to make another video dealing with acceleration here in just a minute, so we'll see you back later. All right, have a great one.